be live. Maybe, maybe not.
Explore biomedical data science and engineering topics. Discover interactive tools and cutting-edge insights into data visualization and signal processing.
Okay, go check out biomedicals.com. There's a lot of tools. Let me know what you think, and you will be supporting the project that way. So thank you in advance for your support. We covered most of this stuff. Yeah, we have this EEG to music conversion. Go check it out. Let me know what you think. You can also do auto volume and auto duration. It will be quieter. So the chart here on the left is auto scaling. See, this frequency spectrum is changing. There's a trend, wavelet. The noise that's actually coming from another tool. You can select your channel. This is 16 channels implanted. So we can guarantee, we are confident that this is actual EEG and not like with external EEG recordings where it could be 50-50. A lot of noise, a lot of artifacts. Yeah, when the auto duration is on, yeah, the duration of the sound will be changed accordingly to the duration of the signal. Yeah, this channel is a bit annoying. Anyway, play around with it, let me know what you think. The trending doesn't do anything because it's already around 0. No, it doesn't look like. Did it just crash on me? Did it just crash on me? Yeah, the denoising is actually in another tool. Should be a separate tool for that, I think. Yeah, it's this one here. So this is similar. It's mainly around denoising. Doesn't have the sound options. This is adding an option for the whole spectrum. Yeah, should limit the window size to something smaller. Something smaller. This is in the middle of the seizure. There is no seizure at the end of the recording there. Anyway, go check out this tool. Let me know if there's any suggestions, improvement. Yeah, I don't know why this tool is a bit heavy. We need to probably redo it. I can hear my server doing extra work that is not needed on loading for some reason. On loading the page, but not and yes, essentially separation value of 0 is the same as the overlay all. So maybe we don't need that function. Don't know why that the screen doesn't become. This is a plotly.js. We can control it using those little things as well, or the bar, the scroll bar at the bottom. Yeah, we could do more work on this one, especially considering how heavy it is on the server. From memory, EG2. So it's IEG2. Yeah, this was the Flask. It's messy. Templates. Right, so we have data sitting on the server. This Neuro Vista data from ieg.org. I think anyone can register and get that data. And now we have what's the HTML for this? Yeah, plot HTML. It's not normally it would be called index HTML. That's okay. It's calling our JavaScript files, doesn't it? A plotly is calling script JS. Okay, I got it. That's the script JS for the whole project. It's for this menu. So don't worry about that. That's the right EG. JavaScript is what doing. Is it most of the work? I don't know what's in. Right. Yeah, a lot of it is in the back end. A lot of it is on the server side, and this is not ideal. Like to can I have the text file, or is it too big? Yeah, I think that data file is way too large. Way too large. Just looking at some. Okay, I might jump around for a bit. Yeah, I'm not sure if I'm. So a lot of this, yeah, problem with showing stuff on the live stream is that a lot of this material is copyrighted. In this case, to like some journal. Don't want to mention the name. Yeah. Well, this article is mainly text. Yeah, LLM will be really good at sorting it out, especially because it has all these acronyms. All I see is acronyms of acronyms. I don't know. Obviously, it was not intended to be read by a normal person. There's only one figure and it's from yeah, I don't know. First thing we do when loading a dataset is checking if they have any published data. They should have like a data availability statement or something. Animal data are difficult to interpret due to species differences. Well, okay. Like, yeah, species make a lot of difference, so despite them, blah blah, this data demonstrates sensitivity, blah blah. There's no data availability. Did they even use any data? Okay, what is the methods? A method section. It's a review article. Biomarkers of humans. Yeah, no, I can't make sense of this paper. Yeah, forget about it. Let's get back to EEG. Someone's saying that the GPT responses are easy to tell. Um, I'm pretty sure even your own responses would not be easy to tell. Like, so, so uh, yeah, yeah. I'm pretty sure yeah. Don't get started on. It's amazing. Yeah, GPT is really good practice of how the human brain can be easily tricked into thinking anything, pretty much. But yeah, don't get me started. Okay, this thing. Let's actually start a new chat. Let's close that. Let's do GPT quickly with this IEG to data. Let's open it quickly in new window. Yeah, it's one that we've been working quite a while. It's called again IEG. Yeah, this one. Yeah, this this project is messy. We will start another one. The description. Let's read the description quickly.
NeuroVista EEG data viewer reviews 16 channels, 8 from each hemisphere, of intracranial EEG, IEEG, sampled at 400 Hz with epileptic seizures recorded using the NeuroVista implant. Use the player or manually scroll through the file using a slider. You can select the active channel and turn it off to hide the trace. Try different overlay options to change how traces are grouped. Off, default, grouped separately for left and right channels, all overlaid on top of each other. The September value sets the amount of separation on the screen, and the window size can be changed from 0 to 60. With 10 seconds being the default. Coming soon, epoch labeling, fuzzy logic, etc. To do, set slider max value programmatically.
Amazing. Yeah. How everything can be a biomarker for depression. Yeah, that article has one figure, and it's called Figure 1. It's good they gave it a number. Let's do this quickly. It's HTML using Plotly latest. JavaScript, that's fine. So what are we calling from here? Yeah, we don't care about that. Script.js. Yeah, EG.js. And this one is running as a Flask application, so we can we run it locally quickly as well? Yeah, it takes forever to load. Why does it take forever to load? It must be that very long file. Can actually limit the data size. Right, yeah. We need to take that data and only have a subsection of that data, or make the whole thing faster. The data is quite large, is it? Shouldn't be too bad. Right, that text file is 2 GB, but surely it's not just loading. Surely it's not just loading into the model, into the Flask application, is it? We need it in static or something. You need to change the whole structure. Okay, we have the info. Yeah, let's do it again. Sorry. Let's do it again quickly. We have the backend, have the HTML with some description, and we have the JavaScript. Let's not prompt it too much, just give it a code. See what we get. See what we get.
The code snippet you provided sets up a Flask application to visualize EEG data using Plotly. It reads data from a file, processes it based on a specified time range, and plots it on a web interface. Here are some improvements and notes on our implementation. Code optimization and cleanup. Data frame column assignment. When renaming your columns, you can simplify the process by including time in your channel underscore names list directly. This makes the column assignment cleaner. NumPy to list conversion. Instead of iterating through each trace in the figures dictionary to convert NumPy arrays to lists, you can use a more concise approach using list comprehensions or a helper function. Error handling in Flask routes. You've handled exceptions well, but consider logging the stack trace only in debug mode or writing it to log file to keep the console output cleaner for production. Use of global variables in JavaScript. Your JavaScript code uses global variables and functions directly. Consider encapsulating them in a module or a class to avoid potential conflicts and enhance maintainability. Repeated code in JavaScript. The function update separation contains repeated code for different cases, grouped, overlay all. This can be refactored to reduce redundancy and improve clarity. HTML and JavaScript separation. Keep JavaScript code out of the HTML file as much as possible by placing it in separate JS files. This enhances readability and maintainability.
Not yet, don't worry about that. Let's use GitHub Copilot as well. With workspace handle. Yeah, it's generating the whole thing, including to do. Okay, we don't want to change this. We want to start fresh. Can you generate all the prompts required to regenerate this web application code? I hope it doesn't do the code generation. Okay, it looks legit.
Create a Python Flask web application that serves an HTML page to visualize EEG data. The application should read EEG data from a local file, process it to display specific intervals, and then use Plotly to generate an interactive plot. The data file is a whitespace delimited text file containing multiple EEG channels. The application should also have routes to serve the plot data dynamically as JSON for updates without page refresh. Write a Python function using pandas to load and process EEG data from a file. The function should read a specified number of rows starting from a given row offset, corresponding to a time slice in EEG data. The data consists of 16 channels plus a time column. Assign column names to the data frame, calculate time in seconds for the x-axis, and prepare the data for plotting. Develop a Python function to create a Plotly line plot from a pandas data frame containing EEG data. The function should plot all EEG channels against time, format the axes and labels, and make the plot interactive with a range slider for exploring data across time. The plot should be converted to dictionary format to be easily served as JSON. Design an HTML template for displaying EEG data using Plotly in a Flask web application. Include elements for the plot, navigation, and interactive controls like sliders or buttons to adjust the display settings of the plot. The template should be responsive and include links to necessary CSS and JavaScript files for styling and functionality. Write JavaScript to enhance the EEG data visualization web page. The script should handle fetching new data from the Flask server, updating the plot dynamically without a full page refresh, and responding to user inputs such as range sliders or options to change the plot display. Include error handling for failed data fetches. Create a CSS file to style the EEG data visualization page. Focus on layout, colors, and responsiveness to ensure the page is accessible and visually appealing across different devices. Style elements like headers, plot containers, and controls to provide a clean and professional user experience. Each of these prompts is aimed at building a specific part of the web application, ensuring that you can manage the development process step by step and make adjustments as needed based on the features and user interactions you want to include.
Yeah, there was a better way of, let's start a new web application. We have a we have an EEG viewer. What shall we call it? Yes, we have the noise removal. Yeah, there were like some really bad names. This one's just called Spectrogram, also not a great name. Just go for EEG view. Let's see what we can do with the data. Don't particularly like this name, but info text. Let's also add the prompt text as well. On a Flask application. What's the description? Let's pop those as prompts. What's the way? Okay, I'll start prompting from there. So where these responses are coming from. Let's write this simple. It's not generating the whole. Yeah, that's better. It's still doing that. I don't like it. So the data can the data be served as JSON as static deployment. Yeah, it's continuing with the problem is that the data file is the problem is that the data file is 2 gigabyte text file. Yeah, why not load it into cache, but that's too much for caching, isn't it? Yeah, understand.
Handling a 2 GB text file containing EEG data efficiently in a web application context requires careful consideration of both performance and scalability. Let's evaluate each of your proposed methods to determine the most suitable approach. 1. Loading data into memory. Pros. Fastest read access once data is loaded. Immediate responsiveness for data processing and visualization. Cons. Not scalable for larger files or multiple concurrent users, and it could exhaust the server's memory. Not persistent. Data would need to be reloaded on each application restart or deployment. Verdict. Loading the entire file into memory is generally not advisable due to scalability and efficiency concerns, especially under the constraint of potentially multiple users or large data sizes. 2. Loading data into a database. Pros. Efficient handling of large datasets through optimized queries and indexing. Scalability to handle larger data sizes and more concurrent users. Data persistence and the possibility of transactional data management. Cons. Requires setting up and maintaining a database system. Overhead of integrating the database with your application. Verdict. Loading the data into a database is a robust solution for large datasets. It allows efficient querying and can significantly reduce memory usage on your web server. This is typically the preferred approach for handling large, structured datasets like EEG data. 3. Loading data into cache. Pros. Fast access for frequently accessed data. Reduces load times after the initial cache build. Cons. Similar to in-memory storage, they may not be feasible for very large datasets without sufficient memory. Requires a strategy for cache invalidation and rebuilding. Verdict. Caching is useful for frequently accessed portions of the data, but is not suitable as the sole method for managing a 2 GB dataset. It's often used in conjunction with database storage, caching results of common queries to improve performance. Loading data into a file system. Pros. Simple to implement, no need for additional systems. Data is persistently stored and managed by the OS. Cons. Direct file access is slower, especially for large files and complex queries. Requires manual handling of file reads, potentially leading to inefficient data processing. Verdict. Keeping the data in the file system and reading chunks of data as needed, e.g., using memory mapped files or efficient on-the-fly parsing, can be viable for small applications or when database setup is infeasible. However, it's generally less efficient than database solutions. Recommended approach. For a 2 GB EEG data file, using a database is recommended. Here's why. Efficiency. Databases are designed to handle large amounts of data efficiently. Functionality. Advanced querying, indexing, and data management features. Scalability. Easier to scale with increasing data size and user load. Integration. Many tools and libraries are available for integrating databases with web applications. Consider using a relational database like PostgreSQL or a time series database like InfluxDB, which can be particularly effective for timestamp data like EEG recordings. By importing the data into the database, you can leverage SQL queries or specialized time series queries to fetch only the required slices of data dynamically, based on user interaction with your application. This approach significantly reduces memory overhead and improves the responsiveness and scalability of your application.
So where's the text file for the EEG data? Should be stored in a separate data folder or in the static folder? This is actually for Copilot. Oh yeah, that's what I'm doing at the moment, but it's super slow. This is what I'm doing at the moment, but the web application is very slow to start. So we're doing this one here. Yeah, it's starting forever. I have it running locally as well. This also takes some time for it to load. Yeah, I have that weird thing happening in the beginning. Yeah, we need to rewrite the whole thing. Yeah, loading 2 GB of file into memory every time the Flask application starts, so that can be slow. Suggesting to load the data into a database. Yes, what else we've got? Database, yeah, different SQL types, caching. If the data doesn't change often, no, it doesn't change often. Loaded into cache like Redis, yeah, I don't know. Chunked reading, if you need to keep the data, if you need to keep the data in a file, consider reading chunks. You can use pandas. Yeah, that's what I thought we were doing, but still takes some time to read portions of the file at a time. This way you only load into memory the data you need for each request. So it's still doing back and forth with the server. If the data is not used frequently, keeping it on file system and reading it only when necessary could be a viable option. This will be slower than the other options, but would keep the application's memory usage low. Hey, can you update all the prompts? Yep. Yeah, just updating the prompts. We're not generating code using GPT. Okay, we have the prompts. The data file is actually called something else. Should be simple. Yeah, I was using only this one file. Where are the, I don't know where the labels are for this data set. I don't think they are in the text file. There should be a separate labels file to look it up. The HTML. generate the HTML code for this application. Doing it in the Copilot. Yeah, this is generic. Generic stuff. Why it's not there? Generate a description for the whole web application. Yep. Need it in info there. I'm still trying to figure out how Copilot is working in terms of like how it's being implemented. Can you explain the whole project? Let's give me generic stuff.
Here's a comprehensive description for the entire web application designed to visualize EEG data, suitable for your project documentation or as an overview for development purposes. Web application for EEG data visualization. Objective. The application aims to provide a robust platform for visualizing electroencephalogram EEG data, facilitating the exploration and analysis of neural signals. This tool is designed to assist researchers, clinicians, and educators in examining complex EEG datasets efficiently. Features: 1. Dynamic data loading. The application does not load the entire dataset into memory, preventing system overload and ensuring scalability. Instead, it accesses data on demand from a database optimized for large datasets. 2. Database integration. EEG data is stored in a structured format within a relational or time series database, which enables efficient querying, indexing, and retrieval. This approach accommodates rapid access to segments of data based on user-defined parameters. 3. Interactive visualization. Utilizing Plotly for
I
the
like
front end, the
how
application presents interactive line plots that display
this
multiple
deep,
EEG channels
deep
over time.
breathing.
Users can zoom, pan, and select specific time windows to closely inspect the data. 4. Caching for performance. Frequently accessed data segments are cached using Redis, enhancing retrieval speed and reducing database load for common queries. 5. File system data handling for archival data. Rarely accessed, historical EEG data is managed directly from the file system, where it is read in chunks to minimize memory usage, ensuring the application remains efficient without compromising on data accessibility. 6. Asynchronous operations. The application leverages asynchronous programming to handle data operations without blocking the user interface, thus maintaining a responsive experience even during extensive data processing tasks. 7. Customizable user interface. A user-friendly web interface allows users to select EEG channels, adjust visualization parameters, and manipulate the view of the data. It includes controls such as sliders for time range selection and options for overlaying multiple channels. 8. Performance monitoring. Embedded performance monitoring tools track and log the application's operations, identifying bottlenecks and allowing for continuous optimization of both backend and front-end components. Technology stack. Backend. Flask, Python, handling routing and server-side logic. Database, PostgreSQL or InfluxDB for data storage and management. Front end, HTML, CSS, and JavaScript with Plotly.js for data visualization. Caching, Redis for caching frequently accessed data. Deployment, containerized using Docker and deployed on a cloud platform for scalability and ease of maintenance. Security measures, rigorous input validation to prevent SQL injection and other common security threats. Secure connection protocols and data encryption to protect sensitive data during transmission. Future enhancements, implementation of machine learning models to predict trends or anomalies within the EEG data. Expansion of interactive features, including real-time data streaming and collaborative annotation tools. Enhanced mobile responsiveness and accessibility features to broaden user engagement. This description outlines the application's core functionalities, the technologies employed, and the strategic approaches to data handling and user interaction. It serves as a blueprint for development and a guide for potential users to understand the capabilities and benefits of the tool.
Yeah, so the Flask application is good because it's essentially not relying on the back end. Wait a second, no. We have, oh, that's incorrect. We do have loading EG data. Wait, is Plotly Express? Taking it from the previous application? I'm not sure. Where is it getting it from? Yeah, obviously different ways to prompt the GPT. It's interesting. So the OpenAI one is just generating prompts essentially for GitHub Copilot. That was the idea. I thought we're not going for database. I thought we're going for local storage, which can be a database, but don't quite understand. Yeah, I have like 2 gig data file to store it somewhere. And let's delete this prompt file for a sec. We should have everything in these 260 lines. The description.
Here's a comprehensive description for the entire web application designed to visualize EEG data, suitable for your project documentation or as an overview for development purposes. Web application for EEG data visualization. Objective. The application aims to provide a robust platform for visualizing electroencephalogram EEG data, facilitating the exploration and analysis of neural signals. This tool is designed to assist researchers, clinicians, and educators in examining complex EEG datasets efficiently. Features: 1. Dynamic data loading. The application does not load the entire dataset into memory, preventing system overload and ensuring scalability. Instead, it accesses data on demand from a database optimized for large datasets. 2. Database integration. EEG data is stored in a structured format within a relational or time series database, which enables efficient querying, indexing, and retrieval. This approach accommodates rapid access to segments of data based on user-defined parameters. 3. Interactive visualization. Utilizing Plotly for the front end, the application presents interactive line plots that display multiple EEG channels over time. Users can zoom, pan, and select specific time windows to closely inspect the data. 4. Caching for performance. Frequently accessed data segments are cached using Redis, enhancing retrieval speed and reducing database load for common queries. 5. File system data handling for archival data. Rarely accessed, historical EEG data is managed directly from the file system, where it is read in chunks to minimize memory usage, ensuring the application remains efficient without compromising on data accessibility. 6. Asynchronous operations. The application leverages asynchronous programming to handle data operations without blocking the user interface, thus maintaining a responsive experience even during extensive data processing tasks. 7. Customizable user interface. A user-friendly web interface allows users to select EEG channels, adjust visualization parameters, and manipulate the view of the data. It includes controls such as sliders for time range selection and options for overlaying multiple channels. 8. Performance monitoring. Embedded performance monitoring tools track and log the application's operations, identifying bottlenecks and allowing for continuous optimization of both backend and front-end components. Technology stack. Backend. Flask, Python, handling routing and server-side logic. Database, PostgreSQL or InfluxDB for data storage and management. Frontend, HTML, CSS, and JavaScript with Plotly.js for data visualization. Caching, Redis for caching frequently accessed data. Deployment, containerized using Docker and deployed on a cloud platform for scalability and ease of maintenance. Security measures, rigorous input validation to prevent SQL injection and other common security threats. Secure connection protocols and data encryption to protect sensitive data during transmission. Future enhancements, implementation of machine learning models to predict trends or anomalies within the EEG data. Expansion of interactive features, including real-time data streaming and collaborative annotation tools. Enhanced mobile responsiveness and accessibility features to broaden user engagement. This description outlines the application's core functionalities, the technologies employed, and the strategic approaches to data handling and user interaction. It serves as a blueprint for development and a guide for potential users to understand the capabilities and benefits of the tool.
Drop. Now we don't want to drop that. Let's see. Sure. Yes, that's what we have in the Ava app. There's all sorts of problems with it, mainly that it's slow. Still need the overlay option and a scroller. I like that scroller. Generate the structure for this project in terms of the files and folders. Make sure we have a functional Flask application. Provide more details. How do we store, and retrieve the data file? We want to make sure that the web application is fast. Yep. What? Okay, maybe a more basic project structure.
To ensure the EEG data visualization web application is efficiently structured, fast, and functional, let's design a clear project directory structure along with details on data handling strategies, focusing on performance and scalability. Here's a detailed setup. Data storage and retrieval. Database setup. Use a relational database like PostgreSQL or a time series database like InfluxDB. Models.py defines the SQL alchemy or models that map EEG data structures to database tables. Data loading strategy. Initial data import. Use a script or a background job to pass the 2 GB EEG file and load data into the database. This process should chunk the data to avoid memory overflow and ensure transaction integrity. Indexing. Apply indexing on timestamps and other frequently queried fields to speed up data retrieval. Partial loading. Instead of loading entire datasets for each request, use SQL queries to fetch only the required segments based on user input, e.g., time range. Caching. Implement caching with Redis for most frequently accessed data. The cache is checked before querying the database, which significantly reduces load times. Flask application setup. Flask app initialization, __init__.py. Set up the Flask application and its configurations. Initialize the database connection. Register blueprints for modular architecture. Routes and views, routes.py. Define endpoints for serving the EEG plot and data. Use asynchronous fetching and processing where necessary to keep the UI responsive. Utility functions, utilities.py. Include functions for EEG data processing, like filtering and segmenting data before sending it to the front end. Front end, static and templates. JavaScript, handle dynamic data loading and updates to the Plotly graph without reloading the page. CSS, ensure the application is visually appealing and responsive across devices. Running the application, run.py, configure and launch the Flask application, ensuring all routes and configurations are loaded. Configuration, config.py, manage different configurations for development, testing, and production environments, such as database credentials and secret keys. Testing, tests, implement tests to ensure the application functions correctly under various scenarios. Performance considerations, optimize SQL queries and use database functions to minimize data processing in Python. Regularly profile the application to identify and resolve bottlenecks. This structured approach not only provides a blueprint for developing a scalable and efficient web application, but also ensures maintainability and ease of development by clearly separating concerns and functionality across different parts of the application.
I'm thinking making the file shorter, just 100 seconds of data. Would that help? The eventual result should be something like the image attached. Are you gonna be generating prompts for GitHub Copilot to actually do the coding, or would you stop being lazy and generate the code as well? Yep.
Given the simpler structure you're aiming for and the request to handle a reduced dataset, 100 seconds of data, your file and folder setup looks good for a streamlined Flask application. Here's how you can effectively manage this project.
Yeah, I had some others a way of loading the data in this is loading pretty quickly. It's running in the browser and everything. It was loading in no time. I like that. Plotly Express. So what we have is the same, but the JavaScript. So where's the bottleneck? Where is the bottleneck? Yeah, I like this one. Like a single unit spike, but this won't be it. So where is all this stuff is being loaded? Obviously, when I use Python alone, it's all loaded on my local machine. Yeah, okay, this does take some time. Yeah, that's very unresponsive as well. So we can have a downsample. Can try that. Unresponsive page. And how much is being loaded in the original? So it's 10,000 data points. What are we loading for the actual application? Number of points to load. It's at 40,000. 40,000. That's why it's so slow. No, it's much quicker. Ah, pa, 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 pa. Could be another seizure in that file. We need to find the label for it. I don't know where the labels are. we want to primarily rely on JavaScript, so the server is not overloaded to save electricity. So essentially we want the backend to do as little as absolutely possible. Can we generate all the necessary code? Starting with JavaScript and then Python code. If we can keep all the Python and JavaScript code in the same Yep.
To align with your goal of minimizing server load and maximizing client-side processing with JavaScript, let's focus on setting up a Flask application that serves the initial data and handles minimal operations on the server. The JavaScript will take care of This JavaScript file will
To align with your goal of minimizing server load and maximizing client-side processing with JavaScript, let's focus on setting up a Flask application that serves the initial data and handles minimal operations on the server. The JavaScript will take care of dynamic data loading, manipulation, and visualization. Here's how you can structure the server-side Python code and client-side JavaScript code. The error message, length mismatch. Expected axis has 1 element, new values have 17 elements, typically occurs in pandas when you try to assign a list or an array of column names that doesn't match the number of columns in the data frame. This often happens during the renaming of data frame columns. Let's address the issue based on your Python script snippet. This error could arise due to a misunderstanding about the data structure when reading the file or incorrect column assignment after reading the data. Debugging the column assignment. In your Flask application, when you read the EEG data file and try to assign column names, ensure that the number of columns you're assigning matches the number of columns actually present in the data frame. If your data frame originally contains only 1 column, which seems to be the case from the error message, but you attempt to assign 17 column names, you'll get this error. Here's how to properly handle the data frame column naming. Check the file's format. Verify the format of the I004_A002_D001_day7.txt file to understand how many columns it actually has. If it's supposed to have 17 columns, ensure that it's being read correctly. Adjust the read method. If the file is tabulated or has a specific delimiter that Pandas isn't automatically recognizing, you need to specify this delimiter when reading the file. If the data is indeed space or whitespace delimited, you might have to confirm there are no issues with the format. Properly assign column names. Ensure you have the correct number of columns before assigning names. Modified code example. Here's a modified version of your server-side data fetching route, with additional debugging and error handling. To adapt the Python and Flask code that serves EEG data using Pandas read_CSV function with chunking, and integrate it with the Plotly Express for visualization, we can follow the pattern you've used in your standalone script. Below is a suggestion on how to implement this in your Flask web application, taking into account the proper usage of September equals S+ as a replacement for the lim_whitespace equals true. Data file and reading. The file is read using the specified skip underscore rows and num underscore points to extract only the relevant portion of the EEG data. This minimizes memory usage and load time. Data columns. Assuming the file contains time followed by 16 EEG channels. Adjust the range in the list comprehension if the number of channels differs. Error handling. Basic error handling is included to catch and return errors during data reading or processing. This JavaScript will handle fetching the data from the Flask server and using Plotly to plot it on the client side. The error you're encountering is caused by a mismatch between the number of columns in the data and the names assigned to them in your Python script. Specifically, it seems that you're attempting to assign 17 column names, 1 for time and 16 for channels, to a data frame that has only 16 columns. This is a common issue when the data frame does not include a separate time column as you might have expected.